Hello students, this is the second lecture and the name of this lecture will be propositions. So let's get started. The name, this chapter is more like an English than a written writing, calculating math. So you can just listen to my lecture and think a lot and don't write a lot of writings. And you have to think a kind of logically, okay? So let's get started. This is the table of contents. We are going to learn about the definition and the proposition and condition and necessary and sufficient condition and the block diagram. So this is the definition of proposition. So what is a proposition? Proposition is a statement which can be decided whether it is true or false. So if it is true, it is a proposition, and if it is false, it is also a proposition. But if it is you cannot tell if it is true or false, then it is not a proposition. So the example: 4 is multiple of 2. Yeah, this is right. So it is a proposition. And let's look at the condition. A condition: a statement which can be decided whether it is true or false by a variable x. For example, px is a condition. Px, x is a multiple of 4. Then this will be covered in the later slide. So let's go on. The statement that is composed of two conditions, assumption and the conclusion, is proposition. For example, this px is a condition that is assumption, and this qx is also a condition which is conclusion. So the example px to qx, it is written in English like this: if x is a multiple of 4, then x is a multiple of 2. So is this right? This is false, but it is, you can tell it is false, so it is a proposition. Let me tell you something. This one dash arrow is just original one, which tells the relationship of px and qx. But when you write this double dash arrow, this means that the left side px and right side qx, then this is the right true proposition. You got it? So when this proposition is true, you write this double dash arrow, and this one dash arrow means that you don't know it is true or false. Okay? So let's go on. Proposition and condition. We're gonna learn about the true state. Do you remember what we learned in the last lecture? We learned about the set. This proposition and condition chapter is also related to the set. So this px condition, this is equivalent to the true set P, and qx is equivalent to true set Q. So the definition is the collection of x that makes condition px true. You say, when this is satisfied, you say the true set of px is large P. This is the name of set. Okay? So, oh, it is written here. The set of Px is denoted by Px. P. Oh, sorry, actually P. And this swung dash right here, the true set of swung dash Px is complementary of set P. This swung dash means not. So let's look at the next word. Oops, is this right? Okay. So, oh, I mentioned this before. Px double dash arrow Qx. If the proposition is true, we use a notation this one. I think double dash arrow is right, I think. And true set guarantee a following relation. Yeah. P is included in Q. So the Venn diagram looks like this. Let's look at the example. If x is a multiple of 6, then x is a multiple of 3. Do you think this is right? This actually is right. Yeah, of course, because it's double dash arrow. So let's write some x's. What do I say? P. This is assumption condition Px, and this is conclusion condition Qx. So the true set of Px is written like this, large P, and the true set of Qx is written like this, Q. So what is included in this set P is that x is multiple of 6, so there might be 6, 12, 18, or 24, blah blah blah, like this. Okay? Are you following me? And Q will be 3, 6, 9, 12, 18. Oh, actually, there might be 15 in the middle. Okay, like this. So, obviously, P is smaller than Q. P is included to Q. So, like in this Venn diagram, I can write some number. 6 will be inside here, and 12, 18, and 24. And in the complementary of P, but inside the Q, there will be some number like 3, 9, 15, 21, like this, so on. So, are you with me? This is where x is multiple of 6. These are the x's. Okay, let's move on. Okay. Px to Qx means P is included in Q. Oh, I mentioned this before. So, let's look at the necessary and sufficient condition. This is very important word for defining the ranges of a relationship of each other. So, if Px condition is, I'll say again, I'm sorry. If this is written, then you can say in English like these two in sentences. First, Px is a sufficient condition for satisfying Qx. So P is inside Q. And the second, Qx is a necessary condition for satisfying Px. So Px, so the sufficient condition and the necessary condition is almost right the opposite. So it is in English. So let's look at the example. A rose is kind of flower. Then this rose grew. Oh, I'm sorry. I'll draw the Venn diagram. This is a group of flower, and this is a group of rose. So then I'll say these two sentences are right here. So in English, this is very important. To be a rose is a sufficient condition for satisfying to be a flower. You got it? It's kind of lingual problem. To be a rose, you have to be a flower, right? So when I say the opposite, to be a flower is a necessary condition for satisfying to be a rose. Is it okay? I bet you understand. So let's go on. If and only if. This means that, what should I call this? Double-sided double dash arrow. Is it right? Oh, I'm very good at naming. Px, double-sided double dash arrow. Qx means that the side is for both sides. So this is true. And no, this erase. And this is true. So do you remember that I mentioned this in the first chapter? If this and this is satisfied, then you can say like this: P and Q is the same set. So let's look at the example. This will be a condition for Px, and this will be condition for Qx. I'll use bold one. Oh, it's too bold. Okay, this is okay. So this is Px, and this is Qx. X is multiple of 2. What do you say to this? Is this same as x is even? I think so. So the true set P will be composed of 2, 4, 6, 8, like this. And Q is composed of 2, 4, 6, 8. These two will be exactly the same. So these two are, we say Px is if and only if Qx. This means these two are exactly the same. This will not that be easy, that hard. You can follow me. Is it? Okay. Block diagram. Finally, this is the last page. It's called block diagram. but this is last but the most important for defining the relationship. We previously learned inverse. My spelling is terrible. Inverse. Okay. So if the original proposition is like this, I abbreviated the x, p to q. Then the inverse is you actually put the knots in both sides. So not p is not q. I'll say this not. A swung dash is very hard. So this is the inverse. Oh, I'll actually write more in a more big word. I'm sorry. Here. I think this is the right position. Inverse is not P to not Q. P to Q, this is the original one. This is the inverse of this proposition, and we have converse and the contraposition. Okay, converse is switching the assumption and the conclusion. So P to Q, the converse of P to Q is Q to P. And the contraposition is doing both of inverse and converse. Is it hard? You might follow me. It is not that hard. So these three are very important. Actually, this is all written in this slide. This was made very hard. We tried a lot hard to make this presentation. So you say this is if this is the original one, then not P to not Q is inverse relationship with the original proposition. And also this converse is Q to P. And contraposition means doing this and this, or the converse first and inverse later. So this is it. And the last but the most important thing I wrote here, and it's not in the slide, but I have to tell you something. The last but the most important thing in this slide is if P to Q is true, which means that P double-sided arrow Q is this is true, then the contraposition of this proposition, which is not QX, PX. Not this. Not PX is also true, which means not Q. Okay, I'll show you this. I actually proved this one for you. If Px to Qx is true, then by the let's say the both true sets are P and Q respectively, then P is included to Q. Is this right? Then if you think about the complementary of the both sets, then you can write like you can say the relationship like this. Is it clear? I can draw the Venn diagram for you. If this is Q and this is P, then the complementary of P is bigger than the complementary of Q. Is it right? So this must have been right. Must be right. This must be right. So if you take this one and change it to the proposition, you come out with this idea, not Q to not P. So the proof end. Is it good? So this is all for today's lecture. I talked about the proposition and condition and the sufficient condition and the necessary condition. These are all important and very basic thing in logic theory. So you have to study hard in your home. And this is it for today. Bye bye.